Hello everybody and welcome back to another Python coding interview question. Today we're going to be doing a medium question from algoexpert.io, which is personally the website I am using and have been using to prepare for coding interviews I have coming up. I'm actually going to be doing a really exciting video soon where I'm going to be doing a mock coding interview with the creator of this website. I believe his name is Clement. I don't know exactly how you say it. I'm going to butcher it, but you guys will see that coming up soon. So if you're excited about that, leave a like. But anyways, the reason I use this platform is not just because, I get paid to use it, which I don't by the people that own this. It's because I actually really like the way that kind of information is presented and how easy it is to quickly go on the website and start practicing your coding skills. You guys know, for me personally, I'm very busy. The last thing I have time to do is search online to find all these different questions and then write my own test cases for them and do it in a Python window on my computer and try to see if I'm correct here. And you guys will see as we go through, it's really easy to save your answers. You can mark them as in progress. You can change your language. You can get some hints like you would get in the regular coding interview. You can set a timer. You have test cases. You know immediately if your code's working or not. And that's kind of what you're paying for when you use this platform. So if you guys do want this, it really is a great resource. I wouldn't recommend it to you if I didn't mean that. And I've used tons of other platforms, and even people have tried to pay me to promote theirs, and I have stuck with this one. So anyways, 10% discount code down below. But let's get started with this question, which is river sizes. Now, river sizes, I'm going to zoom in on this and we'll read through this. Last video, I didn't really go through the question extensively and some people got confused. So let's make sure we really understand this before we dig in. So you were given a two-dimensional array matrix of potentially unequal height and width containing only zeros and ones. That just means, this does not have to be uniform length and width. It could be way longer than it is height-wise anyways. Each zero represents land. Each one represents part of a river. A river consists of any number of ones that are either horizontally or vertically adjacent, but not diagonally. The number of adjacent ones forming a river determine its size. Write a function to return all of the river sizes represented in the input matrix. They do not have to be in order. Okay, so essentially the way that this works is we have these ones here which represent our rivers. And the way that you can kind of think of a river is any ones that are touching each other form a river. And the rivers can be in L's and then go all around, and they don't just have to be straight lines, which is originally what I thought when I read this question. So essentially, for these ones are rivers. So the one on the left side, I'll zoom in maybe a bit more so you guys can see. So this one and this one are river. This one, this one, this one, this one, and this one are river, and they form this kind of L structure like that. So how are we going to go about solving the solution? I'm going to bring up my drawing tablet. We're going to walk through. I'm going to explain my solution. Then we'll code it out here and kind of figure out how this works. All right, so this is an example of what our input matrix might look like. Now I want to start by just identifying the rivers here so you guys understand which ones they are. So we're going to say that this is a river right here. So all of the red underlines. I'll do some different colors so we can see here. I'm going to say that this green is a river right here. And then let's pick another color. Let's go with, purple. We'll say that this one is a river right here. So essentially what we need to do in our code is write some function that's going to be able to look through all of these different ones, this input matrix, and determine the length of all of these rivers. So in this case, we want to have, 3 for this one, we want to have 5, and we want to have 5 for this other river that goes like that. So how can we do this? Well, there's only really a few ways about going to do this that make practical sense. And we're going to want to use a graph traversal algorithm to do this. And I'm going to do this in a depth first search way, and I'll kind of explain how that works and what that algorithm is as we go. But just think about how you might, approach this problem. It's one thing if all you need to find is rivers that go horizontally and vertically. That's actually fairly easy because you can just check every single horizontal row, every single vertical row, and do kind of some comparisons and store the rivers you've already seen. But when we do this and we can have, chains that look something like that as a river, how do we do that? Well, what I'm going to do is a depth first search process. Now, if you don't know what depth first search is, essentially it's kind of looking for a path through a graph. So it's a way to traverse a graph to find the longest path kind of first. Whereas if you're doing a breadth first search way, you're going to iteratively kind of expand outwards. So anyways, we're going to start, and it doesn't matter that this is a 1, but we're going to start by looping through every single position in our matrix. We're going to loop through each row and each column and just look at every single position. That's going to be kind of our first process. What we're going to do is when we get to a position, we're going to see if the element at that position is a 1. If it's a 1, that means we found, the start or maybe possibly even like the middle of a river. And what we're going to do is try to find any river that's attached to it. So like the longest river or whatever river is attached to this one. We're going to try to find that and figure out what the length of that is. So how do we do that? Well, when we find a 1, we found, okay, this is the start of a river, something like that. What we need to do is look at all of the neighbors of this 1 and determine if there's any 1s beside it, because that would be the rest of the river, right? So we're going to look up, we're going to look right, we're going to look down, and we're going to look left. Now, obviously, we can't look left and we can't look up because there's nothing there, so we won't look in those positions. But what we can do is look here at this 0 and look here at this 1. Now, let me just erase all of these so that we have a cleaner thing here. So what we'll do is we'll look at this 0 and we'll say, okay, so is this a 0 or is this a 1? Well, obviously it's a 0. So that means there's no river kind of going this way on the right side. We don't need to continue doing anything past the 0. We'll just stop there. Next, though, what we do is we look at this 1 and we say, okay, so we have a 1, we have another 1. So our river now is of length 2. We've seen both of these 1s. They're part of our river. So what I'm going to do is actually mark the fact that these 1s have been discovered, that we've looked at them, that we've seen them, because currently we have a river of length 2 that contain these 1s. We want to make sure that when we look through, later on in the sequence of this program, we don't reconsider these 1s. So I'm going to create a kind of a set over here. You can think of it as a hash table, think of it as a set. It doesn't really matter. And I'm going to store the position of these 1s. So I'm going to say, okay, so I've looked at this 1. It's in position. What position is it? 0, 0, because that's the position in the matrix, right? So we say that's 0, and then dot, 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 dot. That should be 1, 2, 3, 4, 5. And then 1, 2, 3, 4. Oh, oops, this should be 4. Okay, so we'll say that goes to 4, and we'll do the same thing here to position 4. So we'll say that is, position 0, 0. So we mark that, we say we've seen that 1 already. Now, same thing with the 1. We look at this 1, say, okay, that's a 1. Let's mark this 1. What's that position? That's actually going to be position 1, 0, because we're going to read from the row and then the column after that. Now, the reason we do this is because when we get to this next 1, what we're going to do is continue the process of looking at all the neighbors of this 1, trying to find if this river expands or goes anywhere else. So what we're going to do is, well, we're going to look up, we're going to look left, we're going to look down, and we're going to look right. But now you can see where an issue might occur. If we look up, we're going to see the same river that we've already seen, right? And, well, we don't want to count that river because we've already seen it, we've already marked it, we already know it's part of our river, and we really shouldn't go back to it and start looking in all the different directions from that river. So what we do when we look in all these different directions is we say, okay, well, if we look in this direction and we find a 1 that hasn't yet been marked, that we haven't seen in this set here, only then will we consider it. So in this case, when we go here, we can see that this isn't marked yet, so we consider it. Now, what we're going to do from here is consider all of the neighbors that aren't marked. So in this instance, we'll look at this 1 because this is, one of the neighbors of it. And then same thing from this one. We're going to look in every position. We're going to look for any ones that aren't marked. So we won't look here because that's marked, obviously. So what we'll do then is we'll go to the next one. Then same thing here. We'll go to the next one, continually marking all of these positions in our list. So in this case, we're going to mark position 1, 1. We need to mark position 2, 1, I think. And then we need to mark position, what should this be? 2, 2. I think that's the correct position. Yeah, so we'll go 2, 2 marked. And then this now has made up our first river. We've marked all these positions. And while we've been doing this, we've been keeping track of the length of that river. I don't know what I just wrote there, which I'm going to say is a 5, right? So the length of this river is 5. So we've kept track of that as we've gone through and found all these ones. Now we'll add that to one of the rivers that we found, which is 5. Okay, so we did that. We looked through all of these. So let me erase this and let's talk about the next step that we're going to do. So get rid of all this, all that. Okay, so now we already looked at this one. So we found all these other ones from this one that are connected to it. We've marked all of those. Now we're going to move to this next position, which is a 0. Since it's a 0, we don't need to consider anything because there's obviously no river there. Same thing here. We don't need to consider it. Same thing here. Don't need to consider it. Now we hit another 1. So what do? All right, let's reopen up this set here. Let's start by marking the fact that, okay, we've considered this. Our current river length is 1. We've looked at this 1. What position is this in? That's in position 0, 4. So we'll mark that. Now, what are we going to do? We're going to look left, up, right, down. Right? So we look at all these. We realize that, okay, obviously to the left is a 0. We don't need to look at that. Down, what's that? Oh, it's a 1. Okay, so let's look at that. all right, 1 looks up, looks left, looks right, looks down, sees, okay, well, this one's already marked. We're actually going to mark this one that we've seen it. So what position is this? That's position 1, 4. Then we say, okay, let's go to the next one, which is this one. Let's mark it. What's this one? Well, this should actually be 2, 4. And now our current river length is 3. There's nowhere else that we can go because those are all zeros, obviously. So we stop, we add 3 into our list of rivers. So now we have a list of, let's say, what is it? 5 and 3. So 5, 3. And now we can continue the process. So where did we leave off? Well, we had looked at this one already. So now we'll go to the next one. We'll look at this one. Oh, wait, this is a 1. Okay, so do we start the process again? No, we don't. The reason we don't start the process of looking for other rivers is because we've marked this one and we can see that position should actually be 1, 0, which is right here. So we don't even bother considering it. We go to this one, same thing. It's already in our set, so we don't need to look at it because it's already part of a river. 0, that's a 0, we don't look at it. 0, we don't look at it. 1, okay, well that, we've already looked at it. It's a part of the set, don't look at it, and you guys get the process. 0, don't look at it. 1, don't look at it, it's in the set. 1, don't look at it. 0, don't look at it. 1, it's in the set, we don't care. All of these, obviously, we're not going to look through until eventually we hit this one, say, okay, it's a 1, it's not in the set, so let's consider it, and then we're going to chain, go all the way here, look at all these 1s, mark all these 1s, notice that, that's another river, add 5, then we're at the end here, so we just return that list. And this is exactly what we're going to do, and this is the process that we're going to follow. So I hope that makes sense. I've dug into it pretty in depth. I've talked about it for about 10 minutes, kind of this depth first search approach, which is kind of what this is. We're just looking through all of the neighbors of all these different things and kind of traversing the graph. Now it's time to apply this in Python. It's a little bit of an advanced algorithm, but try to stay with me and, try to write it yourself first and then you come back. Again, AlgoExpert, you can use this question for free. So you guys can actually go to algoexpert.io and perform this question on the website for free. You don't need to sign in or pay for it to do it because this is a free question. Then obviously, if you guys like it, you can take advantage of that discount and use some other questions. Let me put away some of my stuff and we'll get here and start coding. All right, so let's start coding this problem now. I'll make this full screen. Hopefully this is big enough for me or for you guys. Let me know in the comments if it's too small. Actually, we'll go full screen on everything here. Okay, there we go. All right, so what's the first thing that we need to do? Well, we need to create this kind of set that we're going to keep track of all of the marked rivers in. And we also need a list that we're going to keep track of all of the river lengths in that we discover. So what I'm going to do is I'm going to start by creating a set, which we're going to call marked. So this will keep track of all the rivers we've already seen. And now we'll keep track of, rivers that we've seen in a list. What we're going to do next is what I've explained, and I'm just going to follow kind of the algorithm that I explained to you guys in the following page. We're going to loop through every single position in the matrix. So starting from the very top left, going to the very bottom right. So we're going to say for row in range, the length of matrix like that. Then we're going to say for call in range, the len of matrix like this, and then row like so. Now the reason we're doing this is because this is going to essentially tell us how long each row is, because we know these might not necessarily be the same in terms of length and width. So for each row in our matrix, we'll figure out how long that row is and then loop through every single position. Okay, so now that we've done that, the first thing that we need to do is we need to look at the current position in our matrix, so our row call position. We need to see if that's a 1, and we need to make sure that we haven't already looked at it in the marked set. So to do that, we're going to say if, in this case, matrix, and we'll say row call equals 1, and in this case, we'll say row call not in marked. So if that's true, which essentially, again, means, it's a 1 and it's not in the marked set, what do we need to do? Well, we need to start looking at all of the different positions around it. So what we're going to do is start by essentially saying our current river length is equal to 1. At the current moment, we found 1, which means this river has length 1. What we're going to do next is actually set up something that I'm going to call a stack. And I'm going to set up, add this position to marked. Now we'll talk about what this is going to do in a second. So I'm going to say marked.add, and I'm going to add row call, which is essentially saying, okay, we're going to put this position that we've seen in the marked set so we know not to look at it again. And what I'm also going to do is add row call into my stack. Now, if you guys haven't seen stacks before, I'll briefly kind of go through how they work, but it's a fairly simple data structure. This is going to allow us to do kind of a depth first search of this, all the ones that we can find attached to this river. So what I'm going to do now is say while stack, I'm going to say current equals stack dot pop, and we'll talk about what this does. Okay, so what this means is essentially while stack, so if there's anything in our stack. Because what we're going to do is every time we find a 1 that is neighboring the current one that we looked at, we're going to add that to our stack, which we're going to call here, so that we can look at all of the neighbors of that one during the next kind of iteration of this searching, traversing process. So what we do is we're going to say the current node, the current one we're looking at, is going to come from the end of the stack. So whatever we pop off, that's what it's going to come from the end. So in this case, when we start, we'll just get this row column, which is the first one that we have. That's the one we're going to look at. What we're going to do next is get all of the neighbors of this and then look at all of those neighbors and see, what are those neighbors? Are they ones? Are they zeros? Should we look at them? Should we add one to our current river length? Do we see another one that's adjacent to it? What do we do? So what we need to do that though is create a function that can give us all of the neighbors based on a current position in our matrix. So what we're going to do is say define get underscore neighbors, if I could spell neighbors correctly. And I don't know if you spell it O-U-R-S or if it's O-R-S, but we'll just go with this for right now because why not? And what this is going to take is a position and the matrix. What we're going to do in here is essentially find what the position of the left neighbor, the top neighbor, the right neighbor, and the bottom neighbor is. So to do this is pretty straightforward. We're going to just start by saying y comma x equals position, which is just going to decompose this tuple for us and essentially tell us the two components of it so we can use those independently. And now what I'm going to say is if x is greater than, should we say greater than 1? Greater than or equal to 1, what we'll do is, and we'll create a list here, and we'll call it ns, which just stands for neighbors. We're going to say ns dot append, and in this case, we're going to do y x minus 1. Now this is going to give us the left neighbor. So we could put a little comment here that says left, and why am I doing comments in Java? I've been writing too much Java. Next, what we're going to do is check so that was left neighbor, we'll check the right neighbor. So we'll say if x is less than, and in this case, what we're actually going to say is the length of matrix 0 minus 1. Now, the reason we're doing this is because we're going to add 1 to x. So we need to make sure it's less than whatever the length minus 1 is so that we don't get an index error. So we'll say ns dot append y x plus 1. And now we'll do the same thing for y. So if y is less than, or sorry, not less than, greater than or equal to 1, then what we'll do is ns dot append, and we'll say y minus 1 x, and then same thing with the other component. So if y is less than the len of matrix minus 1, because that'll give us the rows, ns dot append, and in this case, this should be y plus 1 x. Now we'll simply return that list, so return ns, and that will give us all of our neighbors. Okay, awesome. So I think that makes sense so far. So now what we'll do is get all of the neighbors of this current position. So to do that, what we'll simply say is, okay, actually we'll say neighbors, why not, equals get underscore neighbors of position, which is actually going to be row call and matrix. Awesome. So now that we do that, we're going to have a list stored in here of all of the neighbors. So what we need to do is look through all of these neighbors. First of all, see if they're 1, see if we've already looked at them or not. And if we haven't, then what we'll do is add 1 to our current river length and then add that to the stack so that we can look at all these neighbors again and again and again and kind of traverse through all of these. And I'll dig into it in a second. So what we're going to do now is say for n in neighbors. So this again will give us those positions. I think I need an H there. I do. Now what we're going to say is if n, or actually I'll say y x equals n just so we can decompose this and make it a little bit easier. So we'll say if matrix, if matrix y x equals 1 and y x not in marked, which essentially means we haven't looked at this river already, then what we'll do is we'll add it to marked. So we'll say marked dot add yx, we'll say cur underscore river underscore length plus equals 1 because this is just another component of the river that we found, so we need to add it. And then finally, what we will do is add it to the stack. So we'll say stack dot append, and if I could get the right symbols here, we will append yx. Now, the reason we're doing this appending to the stack is because we need to add that one. And I think I can go back to my drawing example. Maybe this will make things a bit clearer. Like, okay, well, this is an absolute mess now. But if we're here, right, and we find this other one, well, we need to add this one to the stack so that we can look at the neighbors of this one next, right? And then whenever we find another one, or maybe there's two ones, we add both of them to the stack so that we can look at all of their neighbors during the next iteration when we pop things off the stack. Now, I know this might be kind of confusing to some of you guys if you haven't seen an algorithm like this before, but we're actually almost done. So what we're going to do now is essentially, once this stack is empty, we're going to add to the rivers list. So we're going to say rivers.append current river length, so cur underscore river underscore length, and then at the very end of our program we'll return rivers. Now that should actually be it. I'm just going to do a quick glance at my other screen. I do have the solution up right now to make sure I haven't absolutely butchered it, and it looks like we're doing all right. And yeah, that should actually be it. So essentially the process is, right, loop through every single position, make sure that the position we're looking at is either 1 and it's not marked. If that's true, if it's a 1 and it's not marked, we'll say, okay, so we're going to look for a river now attached to this 1. It has a current river length of 1. We're going to add it to the marked list so we don't look at it again. We're going to create this stack that starts just having this position. Then what we'll do is we'll pop that off the stack, which actually means remove this element, set it equal to current. Then what we do is we're going to say neighbors equals get neighbors row call matrix. So this actually should be current. My bad, guys. This shouldn't be row call. The reason it needs to be current is because we're going to actually change the neighbors we're getting based on the thing we just popped off the stack. So sorry, this is current matrix. This will give us all of the neighbors for that specific position. And assuming I didn't mess up this function, that should be all right. Then what we're going to do is look through all of the neighbors, essentially say, okay, let's break down their components. Let's check if this neighbor is a 1, so if it's a 1 in the matrix, and if it's not yet marked, what we'll do is we'll add it to the marked set. We'll set current river length plus 1 because we just found another 1 that's a part of this river. We'll add it to the stack so that we can then look at all the neighbors of that one and see if there's any other, rivers that are extending and going off. Finally, once that's done, so we don't have nothing left in the stack, we found the end of the river, what we'll do is append the current river length. Then we will return rivers. Now returning rivers will just return this final list. This is a little bit of a messy code, but let's run this and see if we've done all right or not. So let's zoom out, run code, log in to run code. Okay, so I'm going to log in and run the code, and then let's see if this works. Okay, so we passed. Now I would like to say that I actually just had to copy the code, like my solution, back into here. It's the exact same as what I wrote, but you might notice some variable names are a little bit different because for some reason it deleted my code when I signed back in to run the code. Anyways, there we go. We passed. Our outputs are good. And I mean, we can see them. We can have a look at the raw output here saying how long it ran in, and we can have a look at these test cases to see, what we were tested up against and if that actually worked. We can also write our own test cases if we want to inside of your tests, like you can modify them. And if we have a look here, we'll have a look at our optimal space-time complexity. So we have OWH time, OWH space, which is actually, I believe, what this algorithm runs in. So if you guys want to challenge yourself, leave a comment down below and tell me if I'm right or wrong on the space-time complexity of this algorithm. I'm trying to get it centered in the page here so that we can have a look at all of it. But does this that I've written here run in OWH time, where W is the width and H is the length of our matrix? I'm going to go on a limb and say, yes, it does. The reason I say that is because obviously these two loops are going to be WH, right? Then what we're going to do in here is we're only ever going to execute this a maximum of W times H times, because we're adding all these things into our marked set, and looking up an element in a set takes 01 time. On average, it can take longer to find if it's in there, but on average takes 01 time. So what's going to happen is this will only run a maximum of WH times. So technically we would have 2 WH as our maximum amount of runs that we could potentially have, because in combination of all these loops, the sum of that will be less than WH. So we can remove that constant and then have WH as our running time complexity. Now, in terms of space, what we're using is, well, essentially a set here that could potentially have maximum WH elements for every single element being a river. So one massive river is the entire matrix. That's possible. And then rivers here, well, this can have, I mean, in theory, it can have as many rivers as are actually in the matrix. So that's going to give us 2 WH for space. But since, again, we can remove that constant, we'll have WH for space. And that should be good. I'm sure someone could come up with a reason why this might not run in WH, why it might run in like WH squared or something like that. But if you can, that's awesome. Leave a comment down below. And I think that has been it for this video. As always, if you guys enjoyed, make sure to leave a like. You can always get a 10% discount on Algo Expert using the code I have in the description. And with that being said, I will see you guys in another video.